Uli Würfel. Hello, Uli. Hello and welcome on stage. So Uli is from Fraunhofer ISE, one of the really important centers of development of photovoltaic technology in Germany and probably worldwide. And he'll be telling us about development and characterization of ITO-free organic solar cells and modules.
Yes, I'm with Fraunhofer ISE and I'm head of the department which is called Organic and Perovskite Thin Film Photovoltaics. And today I would like to speak about organic photovoltaics for indoor application, show you some stability data, um, show you some results about roll process modules, and then switch over to the topic of highly transparent organic solar cells, and in the end a short note on photoluminescence. I think most of you are well aware of these champions efficiency, how it evaluated over the years and now approaching 20%. One thing to be noted is, of course, that here with the black dots, most of the efficiencies are achieved on rather small areas, mostly well below 0.1 square centimeter actually. And you can see that there is a considerable gap towards efficiencies for cells with larger areas and also on the module scale. So, of course, one of our attempts is to try to reduce that gap. So when we speak about organic PV for indoor application, this was in parts already mentioned by the people speaking before me. A typical light source nowadays is an LED. So we chose a cold white LED as a kind of a standard for us internally. There is no real defined spectrum and intensity, but 500 lux is a typical office lighting intensity. And if you use a cold white LED, then this means that the intensity is about a factor of 700 lower than under one sun conditions. And very important is to have a high parallel resistance. This is shown here in this data. It's quite a busy plot I'll guide you through. So the dashed lines correspond to the Shockley-Queisser limits. So that's an ideal efficiency when you only have radiative recombination. And the red curve corresponds to the AIM 1.5G, whereas the black curve corresponds to a cold white LED with 500 lux intensity. First thing you can note is that the overall theoretical efficiency is much higher for the LED light because the spectrum is much more narrow. And then you can see how the parallel resistance impacts device performance. For the AIM 1.5G, there's a lot of photons available, a lot of current generation, and you can see that if you have a parallel resistance in the range of 2-3 kilo ohm or more square centimeter, you're already safe, you're on the plateau, whereas that's not enough to operate a solar cell decently under the 500 lux conditions. And then the red and the black dots, these were experimentally measured cell efficiencies where we had determined the parallel resistance of these devices. And you can see that they nicely align with what you can expect theoretically. Of course, the efficiencies are much lower than the theoretical limit, but the behavior with respect to the parallel resistance is the same. For example, in the middle, you can see that if you have parallel resistances in the range of 10 to the 4, you're safe under AIM 1.5G. But under 500 lux, these devices suffer severely. Sorry, here. Okay, so we use an ITO-free cell stack, which you can see depicted on the left. As the metal electrode, we use a combination of aluminum and aluminum doped zinc oxide. And as the HDL and front electrode at the same time, we use P.PSS because of the low current generation under the low light, P.PSS conductivity is already enough. And we use a set of different absorber materials, but the results I show now in the following slides are based on PVX Plus, which is commercially available from Renergy Tech, and it can be nicely processed from non-chlorinated solvents. This is a bit older data from our OPV devices when we had compared with crystalline silicon. The nice thing is that the crystalline silicon cell in this case had 25% efficiency under one sun, so it's really a champion device. But due to the much higher thermalization losses of crystalline silicon because of its lower band gap, the efficiency under LED light is much lower. In addition, you can see that it suffers more from the impact of the parallel resistance, whereas our device is still maintaining a very reasonable efficiency down to a low intensity of 50 lux. We also fabricated modules in the same with the same cell architecture and reached very nice efficiencies with this material as well on glass and a bit lower on flexible substrates. So if you want to know more, the paper is indicated there.